In this video, we're going to talk about uniform circular motion, which is a special case of circular motion where alpha, the angular acceleration, is 0, and therefore the angular velocity omega is going to be some constant number. Usually we talk about force with uniform circular motion, but to get there, we first need to understand how angular velocity omega is often found by looking at these things called period and frequency. If you recall, period and frequency are mathematical terms where we use capital T for period, and it is the number of seconds for one thing to occur. Now, inversely, frequency, or lowercase f, is the number of things that happen in 1 second. We can express this relationship by saying that the period, capital T, is equal to 1 over the frequency, f. And we'll do an example to show how that works in just a second. But speaking of seconds, we should talk about the units for these things. Time is in seconds, so period is going to have a unit of seconds. It's pretty easy. But frequency is a little difficult. Frequency is 1 over seconds, and that can be expressed in two other ways. Seconds to the negative 1, or sometimes we call these hertz. Any of those units are useful for a problem with a period or a frequency. So in uniform circular motion, we have a specific thing. That thing is a circle. So thing equals a circle. And a circle has 2 pi radians. So when we want to talk about the angular velocity of an object, we talk about the circle, or 2 pi radians, over the amount of time it takes to make that one circle, capital T, the period. Or, if we prefer, we can think about the angular velocity as a circle, 2 pi, times the frequency that circle happens per second. Either of these equations are useful for finding the angular velocity from period or frequency in a uniform circular motion problem. Let's do an example so that we understand. You spin around 4 times in 1 second before throwing up. How much time did one spin take? Well, this 4 times right here in 1 second, that's per second. That's going to be our frequency. Okay, so that tells me 4 times per second. So I could write that as 4 1 over s, or 4s to the negative 1, but I'm going to write it as 4 hertz right now, just because that's pretty common. And if I want to figure out how much time it takes for one spin, then that's the period, capital T, and I simply take that frequency, and I'm going to do 1 divided by that number. So 1 divided by 4 hertz. And here I'll show what happens to the unit. A hertz is really a 1 over a second. When you have 1 divided by 1 over seconds, then really the second just comes back up on top. And so I'm going to get 1/4 seconds. Or some of you might want to write that as 0.25. Now, I will say this. I picked easy numbers because a lot of you probably could have just done this in your head. If you spin around 4 times in 1 second and you want to know how much time it took, then you probably just took that second and divided it by 4. And that's exactly what we're doing with this equation. Okay, so what was your angular velocity? Well, now we can pick either the frequency or the period to give us this number. All we have to do is take 2 pi and either multiply it by the frequency or divide by the period. I'm going to multiply by the frequency because that one looks a lot easier to do with than the period. So 2 pi times the frequency is going to be 2 pi times 4, which will give me 8 pi. And this is going to be radians per second. That's what the hertz and the 2 pi will turn into. And the number that we usually get for that, if we wanted to put in our calculators, would be about 25.13. Now, you might already think to yourself, wait, how did that unit work? So to show this a little bit better, let's go the other way. Let's say angular velocity is 2 pi over the period. This will help us see how the units work a little bit better, because if we do this, then what we've got is really 2 pi, and we'll call those radians, over the amount of time it takes for one period, or 0.25 seconds. And so that gives you the radian per second right there. And of course, if I divide 2 by 1/4, then that still becomes 8 pi, which would turn into 25.13 if you put it in your calculator. So this way is a little bit easier, I think, to see exactly how that's working with the units, but we have to remember that radians are not necessarily a unit, and if we tried to do this in degrees, then we couldn't put 2 pi on top. We'd have to put 360, and then it would be 360 degrees per second. Okay, now let's talk about angular and tangential velocity. So here, to discuss angular versus tangential velocity, we have 2 bugs on a platform that's about to rotate. We're going to give it an angular velocity of 50 degrees per second, and we're going to let it fly. Okay, so the two bugs are moving, and the question that we have is, which bug is moving faster? And I can maybe increase these a little bit, can go a little bit faster, maybe even a little bit faster. Oh, let's pick it up some more. Oh, that's a good one right there. Which bug is moving faster? The inner bug is completing the same number of rotations as the outer bug, the green one, every second. And so, in a way, they're moving with the same speed because they're both completing the same number of rotations per second. But it's pretty clear that the green bug is moving a little bit faster because it's covering a lot more distance in its circumference. So let's take a look at a problem that helps us understand these ideas mathematically. To begin, angular velocity, omega, is the same for all points or all objects on a rotating body. So the same for all points on rotating body. Sometimes we say that the body has to be rigid because if you're swinging like maybe a foam sword or a whip, then all the points on that object, since it's bending, might have different angular velocities. But if it's a rigid object, they're all the same. But the linear velocity, dealing with the circumference v, is different. We'll talk about why in just a second, but this is often called in rotational motion vt for tangential velocity. But it's the same velocity that you've been using all year, and it uses a very simple idea, and that is the circumference divided by the amount of time for one thing. So the circumference is 2 pi r. So whatever the radius of the circle is, 2 pi r, that's the distance covered. And if you divide that by the period, capital T, then that's going to give you the tangential velocity. If we want, we can also plug in the idea for frequency and say that the tangential or the linear velocity is 2 pi r times the frequency, lowercase f. Now before we get into an example problem, let's notice something here. This 2 pi over t right here, that is the angular velocity. And 2 pi times f, that is the angular velocity. So we can also write these equations that linear velocity is equal to the angular velocity times r. Or I guess this just says the same thing, angular velocity times r. Yeah, so no other one. That's it. That's the relationship. Boom. All of these are useful equations in uniform circular motion. Now, it is worth noting that sometimes the tangential velocity is called v lowercase t, and sometimes the tangential velocity isn't given a subscript at all, and it's just referred to as the velocity or the linear velocity. It's up to you what you would like to use. Let's do an example problem to help sink this in. Two bugs are chilling on a vinyl record spinning 33.3 RPMs. Which bug is moving faster? So this is the problem that we were looking at before in the demonstration. And I've written two radii down for the bugs, the green and the red, so that we can actually get some numbers out of this. So we've already established that the angular velocity for them is both. And so we kind of want to say that they're moving the same speed because the angular velocity for both is going to be 33.3 RPMs, which if you've never heard this before, this is what record players spin at. That is 33.3 repeating revolutions per 1 minute. That both of them are going to have that angular velocity, but they'll have different linear velocities. So the linear velocity of the first object is going to be that angular velocity times its radius. But rather than using that easy equation, let's go ahead and prove it to ourselves with the circumference. The circumference of that red bug is going to be 2 pi r, but we'll use r1. So we'll divide that by capital T, which we need to know somehow from the problem. We can get that number pretty easily by remembering that the period is equal to the angular velocity is equal to 2 pi over t. And so we can use this number, 33.3, to find our period t here on the bottom. But to do so, the first thing we have to do is we have to do this in seconds. So we're going to multiply 1 minute by 60 seconds, get the minutes ready, or rid of the minutes, and this will give us an angular frequency of 3.49. Okay, call it per seconds, that'll be hertz. And then when we want to find the period, Then we'll do 2 pi divided by the angular frequency. So that equation we just used. And we get 2 pi over that 3.49, and that's going to give us 1.8 seconds. Okay. If you feel like you didn't necessarily follow that example, that's fine. We just wanted to get a period for this problem so that we can do it with the linear velocity. But we could have just taken this number in angular velocity and multiplied it by the radius if we want to. But again, lots of different options. Okay, so linear velocity of this bug, we've got 2 pi times the radius of 0.1, so 0.1 meters, divided by the amount of time it takes, 1.8 seconds, and that's going to give me 0.35 meters per second. So that's how fast this first bug is moving. The second bug, we'll call this V2, is going to be 2 pi times R2 over capital T. So I'll do 2 pi times its radius, 0.8 meters. Divide that by 1.8 seconds, and I'm going to get 2.79 meters per second. And so I'm going to get rid of this top stuff here so it's a little less cluttered. So we can see that the outer bug, even though they have the same angular velocity, the outer bug is moving faster than the inner bug, but only in a linear sense because it's covering more of a circumference as it goes through each rotation than the red bug does. And again, that relationship is that the linear velocity is equal to angular velocity times the radius. And that will be really useful in uniform circular motion problems, and it will also come back up again when we talk about things like torque and rotational dynamics much later. So in this video we talked about how to find the angular velocity and the tangential or the linear velocity of objects that are rotating in this special thing called uniform circular motion. And we are done. This video is over.